students, so welcome back to the topic of analysis of nonlinear circuit containing MOSFET after the short break. So, we are discussing about what will be the generalized method, whether the signal or the input is applied to the NMOS or PMOS, and we are discussing about the situation when the circuit contains the PMOS and on the other hand the load, as you can see here, it is PMOS and the load it is connected to ground and so and so. Now, let us see some numerical not numerical different situation if the voltage it is changing at the gate, and then what happens. So, for a given value of the gate voltage and the parameters of the device, we understand that how to find the solution, and in case if the voltage it is changing, then what happens to the solution point. In fact, this is similar to whatever we have discussed with the circuit containing BJT. So, let us do the similar kind of exercise, and we will see whenever the differences are there, we will be highlighting that. So, this is the circuit of our consideration, that we do have the N type MOSFET, the signal or the input we are applying at the gate, the source node it is connected to ground, and drain it is connected to towards the positive supply through this resistance called R d. And at the input, so let you consider different situation. In case this input voltage we vary with time, then what happens to the output voltage. So, as we have discussed so far, for a given value of V in, what we can do, we can draw the IV characteristic of the device, or you can say that output port IV characteristic, and so this is IDS versus VDS, and this is of course for a given value of V in, call say V in is equal to V in 1, and the load line it is given by the straight line. So, one point here it is VDS is equal to VDD. So, that point it is referred as VDD and 0 current, and on the other hand this point it is current, it is so voltage it is 0, but then the current is VDD by RD. So, that is the RD here. So, the slope of course is 1 by R with a minus sign, and what we said is that wherever they are intersecting, that gives us the solution point. So, wherever they are intersecting, that gives us the VDS solution, or you may say that the corresponding V out. So, now for a given V in, say V in 1, how do you find the current? So, then we need to consider the input to output characteristic, namely IDS versus VGS, or in this case VGS it is same as V in. So, you may say that this is VGS which is equal to V in, and we know that this is square law, namely K by 2 W into W by L into VGS, sorry, yeah. So, so this equation it is what we say that K by 2 W by L VGS minus VTH square. So, I consider only this part, I am ignoring this 1 plus lambda VDS part. So, for a given value of V in, say this one V in, we do have this current. So, that current is basically defining this level, and then the load line, wherever this load line is intersecting this current, that gives us the corresponding out. So, you may say that starting from this point called V in 1, that gives us IDS 1, and then this IDS 1, it is getting reflected here. And then the corresponding output here, it is out 1. So, now if I vary this voltage, say if I increase this voltage to some other value, say V in 2. So, this is V in 2. So, that gives us different current, say maybe at higher value like this. So, this level of this current, it is IDS 2, and wherever they are intersecting, that gives us the output voltage, namely the VDS. So, that is the V out 2. So, likewise, of course, here you can see that the device, it is almost entering into the triode region, and beyond that, if you do, then of course, there will be heavy nonlinear part. We will be discussing that soon. So, likewise, if I, on the other hand, if we decrease this V in to a smaller value, namely V in 3. So, then the corresponding current here, it is IDS 3, and then this IDS 3, it is producing. So, IDS 3, it is producing another current level here, and the corresponding characteristic curve may be somewhere here. So, this is IDS 3, and wherever they are intersecting, that gives us the other V out called V out 3. So, as you can see that if VGS is higher than threshold voltage VTH, then we can see that this characteristic, it is going up or down, and making this intersection point of the device characteristic with the load line going up and down, but then along this load line, and making the variation of the corresponding output. So, for different values of V in, if I observe the corresponding V out, what we can get, it is input versus rather input to output transfer characteristic. So, you may say that x axis is V in, and then y axis is the corresponding output, and whenever the V in, it is higher than VTH, then the current starts flowing, the voltage, it will be maybe close to VDD, but of course, it starts dropping. But before that, so here, so this is VTH, and beyond this point, the voltage starts deviating from the VDD level. And if the V in is less than VTH, current is 0 here, and then the output, it is of course VDD. So, as we are increasing this V in beyond VTH, this nonlinear characteristic curve, it is basically some extent it makes it nonlinear, but then this part you can say fairly linear. And then if you increase this V in beyond some point, then of course, the device, it will be it may be entering into the the triode region, and incidentally this crossing point, it may be close to 0, but it will not be going to 0. So, you can see that beyond some point this part it will be entering to the nonlinear side. So, here you may say that this portion, this nonlinear portion, it is due to this part, and on the other hand this nonlinear part of the characteristic curve, it is due to the device entering into the triode region. And in between you can get a nice portion of the characteristic curve, namely this portion. Let me use a different color for this part. So, this portion, it is very good part, namely if I change the input here, then the corresponding current variation here, you can say that it is fairly linear with that voltage, and here of course, the load line is linear. So, that makes the input to output relationship, it is fairly linear. Now, the slope of this line, namely change in V out with respect to V in, that gives us the gain. That means, if I vary this this input by some amount, how much the corresponding effect will be observing at the output, that gives us the gain. And as we have discussed for BJT circuit, here this gain, it is it primarily depends on the slope of this line. So, you can think of it as a mirror. Suppose if we are changing the input voltage with respect to a point, say V in 1 here in this case, then if you vary this input centering this V in 1, then based on the slope of this line, you can get the corresponding current change, and that current change is coming here, and then that current change again getting reflected by the load line to the voltage axis. So, you may say that voltage to current variation and then current to voltage variation. So, here the slope of this line, it is basically the change in IDS with respect to VGS, and this is basically defines the transconductance of the device denoted by GM, transconductance. On the other hand, this slope, of course, it is this slope, it is minus 1 by R d. So, this slope, when we say, it is basically voltage to current slope is this one. In other words, current to voltage slope or current to voltage transformation, it is basically R d. So, if I consider slope of this line and then inverse slope of this line, that gives us the voltage gain here. So, the gain here, it becomes actually GM multiplied by R d with of course, a minus sign. So, how do you find the GM? So, that we will see later, but just to give you a hint that if I consider say this IV characteristic, and if I take derivative of this IDS with respect to VGS, I can find what will be the corresponding GM. So, if you use this equation, you can find the expression of GM, it is equal to K W by L into VGS minus VTH. So, if you multiply this GM by this R d, that will be giving you the gain of the circuit. So, in other words, if I say that at the input, instead of giving varying input, if I considered a signal riding on a DC, then at the output we can get signal riding on a DC. So, let me further, instead of complicating these slides further, it is already becomes clumsy. So, let us go to the next slide and start with a fresh look into the circuit. So, what we like to say that, so we already have discussed the input to output transfer characteristic. So, this is the input, and if we vary this one, what kind of output we obtain. So, I will not be further repeating that detail, but you may recall that we got input to output transfer characteristic is like this. So, this is V in and this is V out, and then if you consider that input we are changing with respect to a DC voltage, nothing but say V capital in, and then if we vary with respect to that by some small amount, it may be called small V in, and the corresponding effect what we get at the output is we do have a DC level here called V capital out, and the corresponding signal we may get with respect to that DC level depending on how much the variation we are giving here, and that may be called V out. So, if you are applying input here at the input at the gate or gate to source some signal here, the corresponding effect we are getting at the drain, which is in fact it goes down. So, it goes down first and then it goes up like this. So, yeah. So, this input to output relationship, it can be said that is the gain. So, we may think of that this circuit it can amplify the signal, and yeah. So, this is what we may sorry, instead of going to the amplifier gain, I have framed one numerical problem to find the operating point and so on. So, let us solve this one first, and then we will be going to the notion of gain. So, the next numerical example associated with this circuit is given here. So, let me give some important parameter here to solve the numerical problem. Say we do have VDD, let me use different color. So, say VDD is given to us is a 10 volt. The device parameter say K is say maybe 2 milliampere per volt square, then VTH of the transistor it is say 2 volt, and maybe lambda we can approximate to be 0 to simplify, and now let us see the V in, this capital V small in, if it is say 3 volt, and I need the other information, particularly R d also. So, let you consider this is 4 k. Then with this condition of V in, can you find what will be the V out? So, we need to find the corresponding value of the V out. So, how do we proceed? To start with, we assume the device it is in saturation, and later on of course, we have to verify it, otherwise we have to use triode region equation. So, if I assume the device it is in saturation, so directly then we can write IDS equals to K by 2 W by L into VGS that is actually V in minus V t h square. And okay, I need this W by L information as well. So, for the time being, let us consider W, it is say 20 micron, and L is a 2 micron. So, with that what we are getting here, it is k is equal to 2 milli 10 to the power minus 3, then by 2, W is 20, L is 2, V in is 3 minus V t h and square. So, what we are getting here, it is 10 milliampere. Now, if you see, if 10 milliampere it is flowing through 4 k, then of course, the drop here it is expected to be 40 volt, then of course, then this is not valid. Okay. So, now let we change the value of this resistance. So, this will not work out. So, let you consider this is 0.5 k. Then what will be the situation? So, if I start with this assumption, the device it is in saturation region, and then the currents should be 10 milliampere. So, the voltage drop across this R with 0.5 k, it will be 5 volt. Yeah. So, 5 volt, and we do have 10 volt here. So, we do have 10 volt here. So, the voltage coming here, it is 5 volt, voltage here it is 3 volt. So, now if you consider the gate and the drain voltage, drain it is higher than the gate voltage itself, that means the pinch off it is happening. So, then this equation is valid, and hence you may say that the voltage here V out it will be 5 volt. But of course, with 4 k the device it will not be really in saturation region. In fact, you may recall that we are talking about input to output transfer characteristic curve. It was like this. So, the V in this case V in and combination of this resistance, if it is a 4 k, what we are doing here, it is the device it enters into the triode region. So, that means the device it was actually in this region, deep into this triode region. So, as a result the pinch off it was not happening. This drain voltage it is very close to ground, and then in that case you may say that if this voltage it is close to ground, the current flow on the other hand it is approximately 10 volt minus close to ground divided by whatever 4 k, and in that case the I R is approximately 10 volt minus whatever the V d s it is approximately. So, let me write this is equal. So, 10 volt minus V d s divided by R, and this can be well approximated by 10 volt divided by 4 k. So, that gives us 2.5 milliampere. So, in fact, this is quite different from the required current in the saturation region. So, if you try to correlate the graphical interpretation of the input to output situation, so the device, in fact, let me draw the load line first. So, the load line it is based on the value of the R, we are getting its slope, and whatever the 3 milliampere of current, 3 voltage 3 volt of the gate voltage, the device actually already enters into deep triode region like this. So, even though this current it is expected to be 10 milliampere, but actual current, since it is deep triode region, that is much lower here. So, on the other hand, if you decrease the value of the resistance, in fact that makes this line, the load line, more stiffer, and that makes this corresponding operating point, it is bringing the device into the saturation region. So, which indicates that the combination of the input voltage, then the device characteristic along with W and L and the value of the resistance, supply voltage should be such that that device may be in the sometimes it may be in saturation region, sometimes it may be in triode region. So, anyway, so it is not necessarily true that the device it will be nicely in saturation region by default. So, we have to in fact verify it. Now, let me consider if the input voltage it is changing with time, then what happens. So, in other words, if I say that input it is varying, but instead of giving just variation with time slowly, if we are having a situation where we do have a DC voltage at the input or at the gate. On top of that, if we are giving a signal, so you may say that this is V in, V capital in here, and the blue part, the signal part, it is V in, and at the output corresponding to this DC voltage, we may be getting one DC part. So, this DC part we may call V capital out, and then on top of that we may be having the small signal or the signal out. Now, whenever we are talking about say these two, basically they are representing the DC part, and if you are observing the signal here and signal here, what we said through the input to output transfer characteristic. So, we said suppose input to output transfer characteristic is like this, and so this is V in, which is having DC as well as the small signal part, and here we do have the V out, which is also having DC as well as the small signal part, and let we assume that the V in it is such that it is making the center point almost at the middle of the linear part. So, the V out part it may be nicely coming there. So, this is the V capital out and this is the V capital in, and then here we are changing this V in with respect to time. So, if I say this is the time axis with respect to time, this V in we are changing up and down. So, at the output what we are expecting is, so at the output we are expecting that this will be going down and then up, down and up with respect to time. So, you may say that this is the small signal input, the corresponding effect it is coming here, and as I said that the small signal input to small signal output, that gives us the another transfer characteristic, or in fact you may say that this part, rather this part of the transfer characteristic, if we nicely shift to another graphical representation where x axis is representing only the small signal part, and likewise if the y axis it is representing small signal output part, and then the transfer characteristic curve, input to output transfer characteristic curve, it is such that it is going through the origin. Beyond this, of course, maybe it is having some significant nonlinear part, but as long as it is linear around the Q point, the operating point, maybe we are happy. So, this transfer characteristic curve, it is referred as small signal input to output transfer characteristic curve. On the other hand, this is referred as large signal input to output transfer characteristic curve. In fact, if you see here, this large signal input to output transfer characteristic curve, it is having the capability to represent the small signal input to output behavior, but many a times we prefer to use this one, assuming this operating point is not changing, to simplify the analysis, to simplify the circuit behavior and so and so on. So, if you see here the equivalent situation. So, here the DC part if you drop, which means that this DC voltage we are making it, it is AC ground. Even this part also we are making it ground, and that makes the equivalent circuit, which is referred as the small signal equivalent circuit. So, if you see the equivalent circuit for small signal situation, you may see that at the gate we are applying only the small signal part, namely the small V in part, and at the this VGS, now we will be calling this is small signal VGS. The current here on the other hand, whatever we call it is IDS, now it is small IDS. So, that is equal to it is just GM into VGS. So, which means that this GM, it is basically slope of the VGS to IDS characteristic curve, and that slope it is basically the important parameter to represent this IDS in terms of the VGS part. So, if you see the circuit here, it is just, if I assume that this part it is remaining constant, then you may say that this relationship it is just linear one. And interestingly, of course, rest of the thing it will be linear, particularly the load part, which is R D, and this is connected to, you may say, AC ground. It is not DC ground, but it is connected to AC ground. Source node anyway it is connected to actual ground, and then whatever the voltage it is getting developed here, it is small signal V out. So, if I analyze this circuit, simplified circuit, where the voltage dependent current source it is represented by this one. So, which means IDS is equal to GM into VGS. So, that gives us the output signal here, which is V out equals to this current is flowing through this resistance. So, that makes GM minus GM into RD into VGS. Okay, let me rewrite this part, it is getting clumsy. So, what we are saying that if I analyze this circuit, we can get small V out equals to R d multiplied by the current I d s, but the current is flowing out of this node and the other side it is connected to ground. So, which means that I need to put the minus sign here, because the drop across this one it is having plus here and sorry minus here and then plus here, and this side it is connected to ground. So, the voltage here it is minus R d into I d s. In fact, the I d s expression of the I d s it is G m into V g s, and incidentally V g s it is same as V in. So, we may say that then V out it is, so we can say that V out equals to minus R d into G m into V in. So, that gives us the gain of the circuit, namely V out by V in equals to minus R d into G m. So, what is the this G m? At least we understand that the gain of the circuit, namely voltage gain defined by V out by V in equals to minus G m into R d. So, let me wipe out this slide and discuss with neat notation. So, what we said is that we are applying a signal here and then we do have a DC voltage, and then at the output you are observing the corresponding effect. We do have a DC current I capital D s. In addition to that, we do have small signal current I d s. This I d s part it is due to small signal V in, and the red part it is capital V capital in. So, while these two currents are flowing through this resistor, so both I d s and capital I d s. So, this is capital I d s, they are flowing through this resistance. So, that makes the drop across this R d as V R d plus small V R d. In fact, if you see here this V R d part, this V R d part it is R d multiplied by capital I d s, and the signal part it is on the other hand it is R d into I d s. And this part what we said is the DC part of the V out, rather I should not say exactly DC part, this gives the DC part. In fact, I should say V d d minus this part is the V out part. So, I should say I should not be directly writing like this. We say that this gives us V out. So, we can say that V out is equal to V d d minus this R d into I d s, whereas this part it gives us V out equals to minus R d into I d s. Note that for signal we consider this is a C ground. So, for signal we do not have this V d d part there, and it can be shown that as I say that this I d. So, I d part if you see in terms of V g s. So, if you consider the I v characteristic, namely I small ds containing both DC part as well as the small signal part versus V G S containing both DC part as well as the small signal part. And the characteristic equation, it is let me use this color like this. And if I say that V G S or V in part, it is a remaining almost constant. So, you may say that this is V capital in, and then that gives us the corresponding current here, I capital D S. And with respect to this V in, whenever we change this V G S, so we may say that with respect to this operating point, called operating point, if we vary, then whatever the change we are applying here, let you call V in, and the corresponding effect is coming there to the IDS. We call this current, it is small IDS. So, from here you may say that IDS by VDS, sorry, V in is nothing but the slope of this characteristic curve, or this is equal to change in IDS with respect to change in VGS. In fact, that is what we are defining as GM. And this GM, if you take the derivative of IDS with respect to VGS, as we have just now we have seen that this GM is equal to K into W by L into VGS minus VTH. In fact, we may have different expression. So, the GM is, at least this is one nice form of the GM. So, let us consider one numerical example and try to see what may be the gain. First, we will find the operating point, and then we will find the slope. By the way, the slope of this line, of course, it depends on wherever we are considering, namely, if the center point it is somewhere here, the slope it will be less. If we consider above here, probably the slope it will be more, and so and so. So, based on the DC voltage or the DC operating point, slope may vary, right. So, first thing is that we need to find the operating point, then surrounding that operating point we need to find the corresponding slope. So, as I said that let me try to make an attempt to find gain of an circuit, simple circuit. How do I start? Yeah. So, this is a 10 volt, and let you consider that we are yeah. So, we do have 10 volt here, and then we are applying a signal here. Maybe this is a 3 volt as we have just now considered to find the operating point, the DC condition. So, let it be 3 volt, and let you consider K into W by L, everything together. If I consider this is a maybe 2 milliampere per volt square, and VTH, let you consider 2 volt. Lambda we may consider approximately 0. RD, let you consider 5.5. Otherwise, the device no, we can consider, in fact, we may consider RD equals to say maybe 4K. Note that W by L we have considered along with this K, and then we are taking this parameter is equal to 2 milliampere. Earlier this part it was 2 milliampere and this part it was 10, that is why we are having the device entering into triode region with R d is equal to 4K. So, anyway, with this we need to find what will be the corresponding GM. So, we may try to see what will be the GM. GM is K into W by L into V in or VGS minus VTH. So, what is the value here? We do have 2 milli 10 to the power minus 3, and here we do have 1. So, 3 minus 2 1. So, that is 2 milliampere per volt. So, this is basically change in current with respect to change in voltage. So, that is why its unit is ampere per volt. So, the gain voltage gain is what we said is minus GM into R d, and the GM it is already we said we obtained here it is 2 milli, and R d equals to 4K. So, that gives us a gain of 8 with a minus sign. So, yeah, so that is the gain of the circuit for this operating point. In fact, if you of course, you have to say that we need to verify whether the device it will be really in saturation region or not. Probably we can quickly verify, say if I consider the IDS, capital IDS, the DC current. So, that is let me use the other color. Yeah. So, IDS equals to K W by L by 2 VGS minus VTH square. So, this is what we are having 2 by 2 milliampere per volt square multiplied by this is 1. So, that gives us 1 volt square. So, let me ignore this part, the unit part. So, what we are getting here it is 2 divided by 2, then this is 1. So, that is basically 1 milliampere of current. And once we have this 1 milliampere of current flowing through this device, and if it is flowing through this 4K, then drop across this 4K it is 4 volt. So, that makes this voltage equal to 6 volt. So, we do have 3 volt here DC wise and this is 6 volt. So, definitely that ensures the device it is in saturation region. So, we have picked up appropriate value of the resistance and this voltage. In case if on the other hand if you are making say this is something different. So, for example, if you consider this is 5 volt and then the 5 volt here it will be making this corresponding current it will be very high. In fact, that will be 5 minus 2 that is 3 that is 9 milliampere. If 9 milliampere has to flow through this 4K, then drop across this resistance it will be much higher than 10 volt. As a result, the device it will be entering into the triode region, and hence calculation of the GM following this equation and finding this gain will not be having any meaning. Okay. So, later we will see that how to pick up the appropriate value or combination of the voltages and all. Yeah, so that brings to the I think end of our main topic. So, what we have covered today, it is we have analyzed a nonlinear circuit containing MOSFET. So, both we primarily have discussed with the examples having in MOSFET, but also we have considered one circuit containing P MOSFET. Then we have discussed primarily the common source configuration, and then also we have seen the input to output transfer characteristic of the circuit, and then we have seen that this circuit, it is able to amplify a signal and its gain expression also we have seen, and of course, we have covered, we got some time to cover two numerical problems. One is for finding the solution point, namely the DC operating point. Other one is to find the gain of the circuit. Thank you for listening.